Okay, the objective today is to explain what the Intel manual says about floating point data types. So in the last video, we talked a lot about integer types, there being a negative and a positive one. These are also known as signed and unsigned. So the manual begins, the IA32 architecture defines and operates on three floating point data types. All right, so we got two integer types and three floating point types. We have a single precision one, a double precision one, and a double extended precision floating point. And I wonder if this helps you make a connection for people who are programmers or interested in programming. I wrote here, what are the three types of floats? So that's programmer slang for floating point data types. The data formats for these data types correspond directly to formats specified in the IEEE standard 754. And I wonder if this is the title. It says for binary floating point arithmetic. Now there's a half precision floating point data type supported only for conversion operation with single precision floating data using F116C extensions, and there's the extensions. I put a question mark there because I genuinely do not know what all that is. Google F16C extensions. I'll do that later and see if I can make a video on it. Or maybe in the comments I'll write what I found. But let's keep moving forward here. The table below gives the length, precision, and approximate normalized range that can be represented by each of these data types. Denormal values are also supported in these types. What is a denormal value? Now this chart isn't so bad, not as bad as some of the others. And you know what, let me go ahead and scroll up there real quick and make a comment about this diagram's representation of floating points. I think it's a pretty good one because what you see here is that a floating point can be negative, so there's the sign bit. If this is a 1, you're likely looking at a negative number. But then you'll see another line here for what's called the mantissa, or that is the decimal. And let me jump to another resource to kind of describe this better to you. I suggest you watch a video from Carl Harold on YouTube because he talks about fractional numbers and binary and does a great job. But let me just highlight the important parts. So if I have two binary numbers, if there's a decimal, what I do is I have to flip it. Normally it goes 1, 2, 4, etc. Well, right here it goes the opposite direction, and the part that really blew my mind, right here. This basically is a 1/2 or 0.5 in decimal numbers. Now one of my first questions is why isn't there a ones place here? I do not know the answer to that. But I want to read the comment that I wrote for this video because I think it's a good one. What I basically said is, it hurts my brain to see 0.1 as 1/2 or 0.5. That just makes my brain scream out for mercy. But a big takeaway, I think, is that a double precise floating point with a tons of ones near the right-hand side, it's not necessarily like a very long number such as pi. It's just a very precise number. So up here in his video where he shows you 0.0011, you basically add these up to get this number. And so I think a good way to think of this is a very precise number. Don't think of it as it's a very long number. And I plan on doing another video where I explain my complete misconception here. I'm going to call that video Floating Points in Binary and My Incorrect Conception. Because I thought it would be cool for this number just to be in a regular kind of way, where we take a number, say 8, and then we look at another number, say 20, and then we just put that together as 8.20, aka 8.2. But nope, that's not how those floating points work. So if we scroll down to the other diagram about floating points, they give us the range, but they do it using these exponents, so it's kind of hard to visualize. If you want to do some reading a table practice, you can answer questions like this. How many precision bits are in a double precision data type? So therefore the answer would be 53. There's a note here that says section 4.8 real numbers and floating point formats gives an overview of the IEEE standard 754 floating point formats and defines the terms integer bit, QNAN, SNAN, and denormal value. Now they're going to throw another table at us soon here. says that table shows the floating point encodings for zeros, denormalized finite numbers, normalized finite numbers, infinites, and nans for each of the 3 floating point data types. It also gives a format for the QNAN floating point indefinite value. And you could go to this section to read more about that. Or it says for a discussion of the use of QNAN floating point indefinite values. So for this video series, you have to patiently wait till we get to that section to understand more. The next paragraph reads, for the single precision and double precision formats, only the fraction part of the significand is encoded. The integer is assumed to be 1 for all numbers except 0 and denormalized finite numbers. For the double extended precision format, the integer is contained in bit 63, and the most significant fraction bit is bit 62. Here, the integer is explicitly set to 1 for normalized numbers, infinities, and nans, and to 0 for 0 and denormalized numbers. So what stood out to me on this was only the fraction part of the significand is encoded. I feel this question's kind of rough, but let's give it a try anyways. What part of the float is encoded differently than the first part? And you know what? I think this gives me, asking this question gave me a hint as to why in this other guy's video we didn't go with a 1. We don't need ones place because a 1 over a 1 is... And so that's kind of worthless. So when there is a binary number like 1, 1, 1, 1, that's 1/2 plus 1/4 plus 1/8, etc. If it happened to be just 1 and all of these were zeros, then it's just 1/2, aka 0.5. And so with this question, I think I answered why there wasn't a 1. This whole part is encoded differently than this part because this part is going to be a regular number. 0, 1, 1, 0 is the number 6, because that's 2 plus 4 here, so 6.5 is the number. And the cool thing about learning all this, depending on how old you are or what stage of life you're in, I have to constantly go against what I call my base 10 instinct to understand these things. And I wonder if experts just have a base 2 instinct and how different that must be. Well, before I get off on the tangent, let me scroll down and kind of look at the table. I like that infinite sign right there. And you could pause here and see if you could do a better job than me, but oh my goodness, I'm looking at this table and I just don't understand it. So let me ask questions, specific questions. I could tell you this, you know what teachers hate is when a student says, I don't get it, or can you help me with this? Ask a specific question. So here's a specific one. What is a biased exponent? For me to better understand this table, maybe I should figure out what that means first. Here's a binary question, or a Boolean question. Is the significand everything in the byte except the sign? Or the word, or double word, or whatever, because I'm looking here, we got an integer part and a fraction part. And all of this is over here, while the word sign is over here. Okay, so 3 tables in one video is quite a bit, and it looks like we're not stopping. Unless, okay, it's continued. See that? Well, I plan on Googling these later. The 2 notes says integer bit is implied and not stored for single precision and double precision formats. And the second note says that the fraction for SNAN encodings must be non-zero with the most significant bit 0. Alright, let me wrap up these 3 paragraphs. The exponent of each floating point data type is encoded in biased format. You can see this section and it's called biased exponent. The biasing constant is 15 for the half precision format, 127 for the precision, 1023 for double, 16,000 blah 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 for the double extended precision format. So a good time to ask a question, what is a biased exponent? When storing floating point values in memory, half precision values are stored in 2 consecutive bytes in memory, single precision in 4, double in 8, and double extended precision values are stored in 10 consecutive bytes. So now when I'm thinking about programming, I'm thinking more about a program accessing chunks from memory versus single bytes at a time. And that's why I recommend budding programmers to start with something like this Intel manual. So you can pause here if you need a reread, but it says which floating point value needs 8 consecutive bytes. Well, last paragraph says the single precision and double precision floating point data types are operated on by this x86 FPU. That's a floating point unit. And then all these crazy words and Intel AVX instructions. So those crazy words are just instructions. I think. Sometimes the way English works is weird. I don't know if instructions is a part of just Intel AVX or not. So for more details, I just wrote what is Intel AVX. Now the double extended precision floating point format, that is such a beginning of a sentence. That's tough. This format is only operated on by the x86 FPU. And you can see this section that's called Compatibility of SIMD. I think that stands for Single Input Multiple Data or something like that. But it's compatibility of SIMD and x87 FPU floating point data types. And apparently it's another discussion, maybe not just regular chapter, but you look there for a discussion of the compatibility of single precision and double precision floating point data types, of course, between those extensions. Alright, so thanks for traveling with me on this video's bumpy ride. This section of the Intel manual really inspires a lot of additional research for me to do. But I hope you learned something. Thank you for watching.